Unit 1, ARM7, ARM9, ARM11 processor. So in that, introduction to ARM processor. So first we will see introduction to ARM. ARM means Advanced RISC Machine. It is most widely used 32-bit RISC instruction set architecture. The ARM was originally developed at Acorn Computers Limited of Cambridge, England between 1983 and 1985. It was the first RISC microprocessor developed for commercial use and has some significant differences from subsequent RISC architecture. In 1990, ARM Limited was established as a separate company specifically to widen the exploitation of ARM technology. It was first established as a separate company specifically to widen the exploitation of ARM technology, and it is established as a market leader for low power and cost sensitive embedded application. The ARM is supported by a toolkit which includes an instruction set emulator for hardware modeling and software testing, and benchmarking as an assembler, C, C++, compiler, linker, and a symbolic debugger. The relative simplicity makes it suitable for low power devices. There are variety of versions ARM7, ARM9, ARM11 and Cortex. Approximately 90% of all embedded 32-bit RISC processors are ARMs. It is used extensively in consumer electronics including PDA, mobile phone, digital media and music player, handheld games, calculator, computer peripherals such as hard drives and routers. So the first model had only a 26-bit program counter, limiting the memory space to 64 MB. It is not too much by today's standards but a lot at that time. So in 1990, at that time, are renamed Advanced RISC Machines. ARM now focuses on embedded CPU cores for IP licensing. Almost every silicon manufacturer sells some microcontroller with ARM core. Some even compete with their own designs. Next is processing power with low current consumption. Compact memories, that is 16-bit opcodes. New core with added features, that is Harvard architecture, in that it consists of ARM9, ARM11 Cortex, floating point arithmetic, vector computing, Java language. It has a 32-bit CPU, 3 operated instructions. It is a RISC design. RISC design means few simple instructions. Load or store architecture, instruction operate on the registers, not on the memory. The large register set and pipeline execution. Although with some CISC touches, the multiplication and load store multiple are complex instruction. Now what is the long form of CISC? Complex instruction set computer. And what is RISC? Reduced instruction set computer. So it has a no stack link register instead. PC as a regular register, that is program counter as a regular register. Conditional execution of all the instructions. Flags altered or not by the data processing instructions. And concurrent shifts or the rotations. So this is the outline of ARM. Now we will see what are the features of the ARM processor. So ARM processors are based on RISC architecture, that is a reduced instruction set computer, and it has provided small implementations and very low power consumption. Also, implementation size, performance, and very low power consumption remain the key features in the development of ARM devices. The typical RISC architecture features of ARM are: the first one is large uniform register file. Second, we have already seen it. Second is a load or store architecture where data processing operations only operate on register contents, not directly on the memory contents. The third point is simple addressing mode, with all load or store addresses being determined from the register contents and instruction fields only. Uniform and fixed length instruction field to simplify instruction decode. The next feature is control over both the arithmetic logical unit, that is ALU, and shifter in most data processing instruction to maximize the use of an ALU and a shifter. Next feature, auto increment and auto decrement addressing modes to optimize program loops. Next, load and store multiple instructions to maximize data throughput. The next feature, last feature, is conditional execution of almost all the instructions to maximize execution throughput. Now, next is why ARM? Why ARM is best? So, ARM is advanced RISC machine. We have already seen that it has a low power, low cost, tiny design. It has 18, 16, 32, 64 bit processor. It has a thumb mode, TDMI, that is thumb mode debug interface multiplier IC interface. The ARM is one of the most licensed and thus widespread processor core in the world. It is used especially in portable devices due to low power consumption and reasonable performance. So these are the features of ARM 7 core and its extensions. So first is small number of transistors in ARM 7 core. It has a small number of transistors nearly equal to 35,000. It has no microcode, all instructions hardwired, three-stage pipeline. It has 4 to 8 KB cache memory, typically unified, 32-bit ISA, and 18 to 56 megahertz clock period. Now there are some ARM extensions. It has thumb instruction set, that is 16-bit ISA packed into 32-bit code, and it has Jazz instruction set, that is Java code executed in hardware instead of JVM. Next is ARM architecture. So the ARM 7 processor is based on one human model with a single bus for the data and the instructions. The ARM 9 has Harvard model. Basically there are two models, human architecture and Harvard architecture. ARM 7 is based on one human and ARM 9 on the Harvard. Though this will decrease the performance of ARM, it is overcome by the pipeline concept. ARM uses the Advanced Microcontroller Bus Architecture, that is AMBA bus architecture. This AMBA, that is Advanced Microcontroller Bus Architecture, include two system buses, that is AMBA High Speed Bus and Advanced System Bus, and the Advanced Peripheral AMBA High Speed Bus or Advanced System Bus, and second is Advanced Peripheral Bus. The ARM processor consists of arithmetical logic unit, booth multiplier, barrel shifter, control unit, register file. So it follows the RISC architecture. It is both in von Neumann and Harvard architecture, as ARM7 is based on von Neumann and ARM9 based on the Harvard architecture. It has a 32-bit processor, 32-bit address line. Now features used from RISC design, that is load or store architecture. It has a fixed length 32-bit instruction and 3 address instruction formats. And there are some features which are rejected from the RISC design, that is register windows, delayed branches, and single cycle execution of all instructions. So this is the diagram for architecture of ARM processor. This is the topologies, that is this one is von Neumann architecture and second is Harvard architecture. So ARM7 and older, and here ARM in Harvard architecture it has ARM9 and some new ARMs. So what is von Neumann architecture? The basic difference between the von Neumann and the Harvard architecture. The first point is flexibility. So in von Neumann architecture, it has a high level of flexibility as the memory is shared between the instruction and the data. So the level assigned to each can fluctuate depending on the task. And in Harvard architecture, the limited flexibility, as there is only a certain amount of memory that can be used for data and certain amount for instructions. Next point is speed. In von Neumann architecture, speed is limited when compared to Harvard due to only having one memory location and set of buses. In Harvard architecture, there are two sets of memory and buses, mean the data can be handled more quickly, which will result in decrease in execution time. And the third point is its example. For example, in von Neumann architecture, typically it is used in general purpose computers that will be used for many different purposes. And the Harvard architecture typically embedded system like washing machine, burglar alarm, etc. That is von Neumann architecture consists of common program and code memory, while Harvard architecture consists of separate program and code memory. The execution instruction in von Neumann is relatively slow because not possible to fetch the code and the data simultaneously, while in Harvard execution of the instruction are faster because fetching of the code and the data are separate. In von Neumann, execution instruction take more instruction machine cycle, while in Harvard it takes less instruction machine cycle. Von Neumann it use CISC processor, Harvard use RISC processor. In von Neumann there is no need to parallelism. In Harvard there is a greater amount of parallelism. The largest advantage of von Neumann is that it simplifies the chip design because only one memory is accessed, while in Harvard the chip design is complex because of separate memory. So these are some differences between the von Neumann and the Harvard architecture. So current low-end ARM core for applications like digital mobile phones, TDMI, T that is thumb, 16-bit instruction set, D that is on-chip debug support is provided, enabling the processor to halt in response to a debug request. M that is enhanced multiplier, it yields a full 64-bit result, high performance. And I is embedded CE hardware, von Neumann architecture and the 3-stage pipeline. The next is architecture of ARM processor. So this diagram shows the core diagram, that is architecture of ARM processor. In that it consists of address register, address incrementer, register bank, multiplier, barrel shifter, 32-bit ALU, as well as write data register, the instruction pipeline, read data register, thumb instruction decoder, and on the right side there is an instruction decoder and control logic. Above that there is a scan control. So the ARM processor, basic elements of these ARM processors is arithmetic logic unit, that is ALU, it is 32-bit. Next is booth multiplier, which is also 32-bit. Also barrel shifter, one control unit, and register file of 37 registers, each of 32-bit. In addition to that, ARM processor also consists of a program status register of 32-bit, that is PC of 32-bit. Some special registers like instruction register, memory data for read and write register, memory address register, one priority encoder which is used in multiplier, which is used in multiple load and store instruction to indicate which register file to be loaded or stored, and multiplexers, etc. So the ARM architecture is compatible with all 4 major platform operating system, that is Symbian OS, Palm OS, Windows CE and Linux. ARM is the industry standard embedded processor architecture and is a leader in low power high performance cores. ARM 7 and ARM 9 families have contributed to ARM's success. So each core family has several children that incorporate many different value added features and combinations. Essentially, there are 4 main families available now for license, that is ARM 7, ARM 9, ARM 10 and ARM 11. So next point is ARM family, that is ARM extension family. Now ARM 7 is a group of older 32-bit RISC ARM processor core licensed by ARM Holdings and microcontroller use. The ARM 7 core family consists of ARM 700, ARM 710, ARM 7DI, ARM 710A, ARM 720T, 74T, 71T, 710T, 7TDMI, 7TDMIS, 7EJS. The ARM 7TDMI and 7TDMIS were the most popular core of the family. So in ARM family, the first ARM processor is ARM1. So it is first ARM processor and it has a 26-bit addressing. The second is ARM2. It is 32-bit multiplier and it has a 32-bit compressor support. Next ARM3, it has on-chip cache, atomic swap instruction and it has a compressor 15 for cache management. Next is ARM6 and ARM7DI. It is a 32-bit addressing, separate CPSR and SPSR. It has new modes, undefined instruction and abort. MMU support, virtual memory. Next is ARM7M. It has a signed and unsigned long multiply instruction. The strong arm is next. It has load store instruction for signed and unsigned half words or the bytes. It has new mode system. Reserve SWI space for architecturally defined operations. It has a 26-bit addressing mode no longer supported. Next is advanced, that is ARM7 TDMI and ARM9T. So it has thumb. Next ARM9E and ARM10E. It superset of the ARM-v40. Extra instruction added for changing the state between arm and thumb. Enhanced multiply instructions. Extra DSP type instruction and faster multiply accumulate. Next ARM7 EJ and ARM926 EJ. It has a Java acceleration. And the last is ARM11. It has improved multiplier instruction, unaligned and mixed ending, endian data handling, new multimedia instructions. So this is ARM family. Next is ARM7 TDMI. Now first we will see ARM7. The ARM7 is a RISC computer with small instruction set and consequently a small gate count. This makes it ideal for embedded system. It has high performance, low power consumption and it takes small amount of available silicon die area. The ARM7 core has von Neumann style architecture where both data and instruction use the same bus. The core has 3-stage pipeline and it executes the architecture ARM-v40 instruction set. The ARM7 TDMI was the first new range processor introduced in 1995 by the ARM. It is currently very popular core and used in many 32-bit embedded processor. It provides a good performance to power ratio. The ARM7 TDMI processor core has been licensed by many top semiconductor companies around the world and it is the first core to include the thumb instruction set, a fast multiply instruction and the embedded ICE debug technology. One significant variation in the ARM7 family is ARM7 TDMI-S. The ARM7 TDMI-S has same operating characteristic as standard ARM7 TDMI but is also synthesizable. The ARM7 TDMI, that is ARM7 plus 16-bit thumb plus JTAG debug plus fast multiplier and enhanced ICI. So what is that TDMI? TDMI, T for thumb, it has 16-bit thumb. D for debug, it has a JTAG debug. M for multiplier, it has a fast multiplier. And I for IC, as it is enhanced IC. So this processor implements the ARM v4 instruction set, and it was licensed by the manufacturer by an area of semiconductor companies. In 2009, it was one of the most used ARM cores and is also found in numerous deeply embedded system designs. The Texas Instrument licensed by ARM7 TDMI, which was designed into the Nokia 6110, the first ARM-powered GSM phone. This led to a popular series of Nokia phones using the processor, including 3210 and 3310. So there are some specifications of ARM7 TDMI. It is a versatile processor designed for mobile devices and other low power electronics. This processor architecture is capable of up to 130 MIPS on a typical 0.13 micrometer process. The ARM7 TDMI processor core The ARM7 TDMI processor core implements ARM architecture v40. The processor supports both 32-bit and 16-bit instructions via ARM and thumb instruction set. The ARM licensed the processor to various semiconductor companies which design full chips and based on ARM processor architecture. There are some applications also. The most common piece of the electronic equipment currently used in this processor are the audio controller in Sega Dreamcast, D-Link DSL 604 plus wireless ADSL router, iPod from Apple, iRiver portable digital audio players. Next application is juice box. Next is most of the Nokia's mobile phone range, pocket station. The main CPU is 10 pinball SAM system games. Many automobiles embed ARM7 cores in tournament. In building automation, the American Automatrix BBC SD uses the ARM7 TDMI core. Next is ARM9 family. The ARM9 family consists of hardened macrocells with variants also including cache with MPU. The ARM9 family was announced in 1997. Because of its 5-stage pipeline, the ARM9 processor can run at higher clock frequencies than ARM7 family. The extra stages improves the overall performance of the processor. The memory system has been redesigned to follow the Harvard architecture, which separates the data D and instruction I buses. The first processor in ARM9 family was ARM920T, which includes a separate D plus I cache, that is debug plus I cache, and at MMU. This processor can be used by operating system requiring virtual memory support. The next processor in ARM9 family were based on ARM9ES core. This core is synthesizable version of ARM9 core with E extension. There are two versions, ARM946ES and the ARM966ES. This is important when debugging application with time critical segment. The ARM96ES include TCM cache and an MPU. The latest core in ARM9 product is ARM926EJS synthesizable processor core announced in 2000. It is designed for the use in a small portable Java enabled devices such as 3G phone and a personal digital assistants, that is PDAs. The ARM926EJS is the first ARM processor which core to include the Jazelle technology accelerates which accelerates Java bytecode execution. It features an MMU configurable TCM and D+I cache with 0 or non-zero wait state memories. Now ARM9 processor family, it enables a single processor solution for the microcontroller. The ARM9 DSP enhanced processor are well suited for applications requiring a mix of DSP and microcontroller performance. The ARM9 processor family include ARM926EJS and ARM946ES and ARM968ES processor. ARM9 family is the most popular ARM processor family ever. It has 250 plus silicon license and 100 plus license of ARM926EJS processor. This processor continue to be successfully deployed across a wide range of products and applications. This family offers proven low risk and easy to use design which reduce cost and enable rapid time to market. This family consists of three processors, ARM926EJS, 946ES and 968ES. Now the application, these are at the heart of advanced digital product across the multiple applications. The ARM9 family processor deliver deterministic high performance and flexibility for demanding and cost sensitive embedded applications. The rich DSP extensions available remove the need for separate DSP in the SoC design. In addition, the PPA is ideally suited to wide range of applications. Now, the processors are available in license in number of form. It is cost effective because of this. Available as per users multiple layer terms. Also available as a hard macrons to reduce time to market and design risk. Now difference from ARM7, it is decreased heat production and lower overheating risk. The clock frequency improvement, shifting from a 3-stage pipeline to a 5-stage one lets the clock speed be approximately doubled. on the same silicon fabrication process. Cycle amount the cycle count improvement. Many unmodified ARM7 binaries were measured as taking about 30% fewer cycle to execute on ARM9 core. There are some key improvements which include faster load and stores. Many instructions now cost just one cycle. This is helped by both the modified Harvard architecture and new pipeline stages. Now the comparison of ARM7 TDMI and ARM9 TDMI families. The first one is pipeline comparison. So to decrease the performance, the pipeline of ARM9 TDMI core was re-energized from the third three stages system used by the ARM7 TDMI family to 5 stages. The operations previously performed in the execute stage of ARM7 are spread across 4 stages in the ARM9 pipeline. Decode, execute memory and write. The reorganization and removal of these critical paths resulted in a much higher clock frequency. Next is ARM10 family. The ARM10 was announced in 1999 and it was designed for the performance. It extends the ARM9 pipeline to 6 stages. It also supports an optional vector floating point, that is VFP unit, which add a 7th stage to ARM10 pipeline. The VFP significantly increases the floating point performance and is compliant with IEEE 754.1985 floating point standard. The ARM10-20E is the first processor to use ARM10E core. Like ARM9E, it includes the enhanced E instruction. It has a separate 32KD plus I caches, optional vector floating point and an MMU. The ARM10-20E also has a dual 64-bit bus interface for increased performance. It is similar to ARM926 EJS but with both MPU and MMU. It has Harvard 6-stage pipeline. It supports VST instruction set, embedded ICE RTII debug logic, fully compatible with V40 architecture, 390 to 700 MIPS integer performance based on Drystone 2.1. It has a branch prediction. It eliminates 70% of the branches on typical code sequence. It separates the load and store unit. It has a 64-bit path to register bank. Load 2 registers simultaneously. Hit under miss cache significantly reduces pipeline stalls. It is a write buffer, new energy saving power down modes. The pipeline was widened to add an additional stages and improvements were made to be embedded IC logic to provide support for read-time debug. All the while compatibility was maintained with ARM v5T and v4T for each mode migration. The performance enhancement include the introduction of branch prediction, hit under miss support in the MMU and cache architecture. This feature improves code performance by lowering the average number of cycles per instruction and of the processor, and also help when the code is heavily dependent on cache operations. Next is ARM-11. The ARM is designed for high performance and power efficient applications. ARM1136JS was the first processor implementation to execute architecture ARM v6 instruction. Incorporates an 8-stage pipeline with separate load, store and arithmetic pipelines. The ARM11 is an ARM architecture with 32-bit RISC microprocessor family, which introduced the ARM v6 architectural additions. These include SIMD media instruction, multiprocessor support, and new cache architecture. The implementation included significantly improved instruction processing pipeline compared to previous ARM9 and 10 families, and it is used in smartphones from Apple, Nokia and others. The initial ARM11 core was released to license in 2002. The ARM11 family is currently the only ARM v6 architecture core. There were two only ARM v6 M cores, that is Cortex M0 and Cortex M1, addressing microcontroller application. ARM11 core target more demanding applications. Next is difference from ARM9. Now, based on the instruction set, the ARM11 builds on preceding ARM9 generation. It incorporates ARM926 EJS features and adds ARM v6 instruction for media support, that is SIMD, and accelerating IRQ response. SIMD instruction, which double the MPEG4 and audio digital signal processing algorithm speed cache, is physically addressed, solving many cache aliasing problems and reducing context switch overhead. Microarchitecture improvement in ARM11 core include the SIMD instruction, which can double and audio digital signal processing algorithm speed. Second, cache is physically addressed, solving many cache aliasing problem and reducing context switch overhead, which is already told. Unaligned and mixed endian data access is supported, reduced heat production and lower overheating risk, redesigned pipeline and supporting faster clock speeds. The ARM11 core, there are currently 4 ARM11 cores: ARM1136, ARM1156, which introduced thumb 2 instruction, ARM1176 introduced security extension, and ARM11MP core introduced multi-core support. The ARM11 based chips are Ambarella, Freescale, NVIDIA Tegra, PLX Technology, Qualcomm, Samsung and Texas Instrument. Next is ARM family comparison. So comparison is between ARM7, ARM9, ARM10 and ARM11. So first point is pipeline depth. In ARM 7 there is a 3 stage, ARM 9 5 stage, ARM 10 6 stage and ARM 11 is 8 stage. Next is typical megahertz. For ARM 7 it is 80, ARM 9 150, ARM 10 260 and ARM 11 it is 335. Next is milliwatt per megahertz. It is 0.06 in ARM 7, 1.1 or we can say 0.19 in ARM 9. In ARM 10 it is 1.3 and in ARM 11 it is sorry, in ARM 7 it is 0.06, in ARM 9 it is 0.19, ARM 10 it is 0.5 and ARM 11 it is 0.4. And next is MIPSB per megahertz. For ARM 7 it is 0.97, ARM 9 it is 1.1, 1.3 for ARM 10 and 1.2 for ARM 11. Next is architecture point. ARM 7 architecture is von Neumann and remaining 3 that is ARM 9, 10 and 11 these all are hardware architecture. Next is multiplier. ARM 7 has 8 by 32 multiplier. ARM 9 also 8 by 32. ARM 10 and ARM 11 is 16 by 32 multipliers. Next is in short the ARM family, its year of release. So ARM family, ARM 7, 9, 10, 11. ARM 7 was released in 1995, ARM 9 was in 1997, ARM 10 1999 and ARM 11 in 2003. Architecture, ARM 7 is only based on von Neumann architecture and remaining 3 based on the Harvard architecture. Pipeline, the first one is 3 stage, next 5 stage, 6 stage and 8 stage. Then operational frequency already seen. These all points have already seen in the previous. So these are the points for the comparison. Thank you.